So second problem based on Lagrange's mean value theorem. Second problem based on Lagrange's mean value theorem. This is some tricky problem comparing with the previous problem. Prove that. See the problem. Prove that b minus a by 1 plus b square less than tan b minus tan a by tan a, which is less than b minus a by 1 plus a square, where 0 less than a less than b less than 1. That means a comma b values lies between 0 and 1, and a is less than, strictly less than b. Also, hence deduce that, see here, hence show that after proving this inequality, you by substituting a and b value, we get this inequality. But choose a and b value in a proper manner, then only we get this result. Here, how to choose f of x? Here there is no any f of x in this problem. Previous problem we have a f of x. Now here there is no f of x. But you understand that it is in the form f of b minus f of a by b minus a. B minus a is this side move. Both side move the b minus a as a numerator. So you feel that here f of b is a tan inverse x form. Let see f of x equal to tan inverse x. Based on the providing question, we choose f of x. Therefore, as per mathematics, derivative of tan inverse x is 1 by 1 plus x square. Then by applying the mean value theorem, the formula of mean value theorem is f of b minus f of a by b minus a, which is equal to f dash c, where c is a point lies between a comma b. So substitute the f of b value, because f of x equal to tan inverse x. Therefore, f of b equal to tan inverse b. F of b value is tan inverse b. Similarly, f of a value is tan inverse a by b minus a, denominator as usual, equal to tan inverse f dash c. F dash c equal to derivative of function x is 1 by 1 plus x square. Derivative of function at c means 1 by 1 plus c square. Substitute x equal to c on both sides, left side as well as right side, in this equation. We get f dash of c. This is the equation. We have 1 by c, 1 by 1 plus c square value in terms of tan inverse b minus tan inverse a by b minus a. So these two values are equal. As per hypothesis, they provide a is, now by using Lagrange's mean, as per hypothesis, a is less than b. By the Lagrange's mean value theorem, c lies between a and b. That means a is less than, c is less than b. Squaring the numbers, the inequality also does not change. For example, 2 less than 3 less than 4. Squaring the number in the same manner, or 0.1, 0.2, 0.3. If you take a equal to 0.1, b equal to 0.2, c equal to 0.3, then squaring them, we get the same inequality. A square less than c square less than b square. Adding any number, either positive or negative, inequality does not change. So here I am adding 1, because in the denominator, given expression, denominator we have 1 plus b square, 1 plus c, 1 plus a square. In the left inequality, you observe that here we have 1 plus b square, here we have 1 plus a square. So adding 1 and reciprocate. If you reciprocate the number, we get in the reverse manner, because for example 2 less than 3. Then what about its reciprocal? 1 by 2 is greater than 1 by 3, because 1 by 2 value is 0.5, 1 by 3 value is 0.33. That means 1 by 1 plus a square greater than 1 by 1 plus c square greater than 1 by 1 plus b square. Greater than converted into less than inequalities, it is also written in the form 1 by 1 plus b square less than 1 by 1 plus c square less than 1 by 1 plus a square. From the previous equation, all are greater than relation. They are converted into less than. Just simply you take from here left to right. If you take right to left, we get the less than inequality. Substituting 1 by 1 plus c square value in the equation 2. Already we know the 1 by 1 plus c square value in the equation 1. Tan inverse b minus tan inverse A by B minus A. Substituting middle inequality value 1 by 1 plus C square value, we get 1 by 1 plus B square less than tan inverse B minus tan inverse A by B minus A, which is less than 1 by 1 plus A square. Now you observe that in the goal, B minus A is the numerator for the inequality. So we multiply our resultant inequality. This is our resultant inequality. Multiply this inequality with B minus A. B minus A into 1 by 1 plus B square becomes B minus A by 1 plus B square less than B minus A. Here B minus A get cancelled. In the right hand side inequality term, B minus A by 1 plus A square. Now the resultant inequality becomes B minus A by 1 plus B square less than tan inverse B minus tan inverse A less than B minus A by 1 plus A square. One more thing, you observe that B minus A is positive number, A less than B. A less than B by the hypothesis. That means 0 less than B minus A. Move A to the right hand side, it becomes minus A. So 0 less than B minus A. That means B minus A is a positive number. Whenever we multiply with a positive number, the inequality does not change. That's why the above inequality does not change if we multiply with a positive number. Suppose if you multiply with a negative number, inequality changes in the reverse manner. Suppose if you have less than, it becomes greater than when we multiply with the negative terms. First part of the proof is over. Second part is, and hence deduce that second part, or hence show that pi by 4 plus 3 by 25 less than tan inverse B by 3, which is less than pi by 4 plus 1 by 6. You always, whenever you see this form, pi by 4, we get a pi by 4 by applying the trigonometric inverse functions. That's why pi by 4 sent to middle. You understand that pi by 4, we want to show that this inequality, pi by 4. That means 3 by 25 less than tan inverse pi by 4 minus pi by 4 less than 1 by 6. Subtracting pi by 4 from the inequality. So pi by 4 value nothing but tan inverse 1. That means you always converted into our required format. This is our intention. By choosing values, guessing the values, for the guessing the A comma B values, that point of view, I convert the output in terms of our required format. So B value is, here B value is 4 by 3, A value is 1. Substituting or put B equal to 1 by 4 by 3, A equal to 1 by A equal to 1 in the above proved result. Our proved result is B minus A by 1 plus B square, which is less than tan inverse B minus tan inverse A less than B minus A by 1 plus A square. Substituting B value is 1 by 4 by 3, A value is 1 throughout the inequality. Finally, we get the required answer in this manner. Okay, this is important problem. So next form of the Lagrange's mean value theorem have two forms. This is second form of the Lagrange's mean value theorem. It is very easy. Just replace Lagrange's mean value theorem, second form. B is taken as A plus H because A is smaller than B value. Always A is less than B. By adding some value, we get a B. Adding some positive value. For example, here 2, here 5. By adding 3 to the 2, we get 5. Adding 3 to the 2, we get 5. Here also, adding some value H, we don't know how much, what is the value of H. Adding H to A, we get B. So that's why by adding H to A, we get B. C is a intermediate value. By Lagrange's mean value theorem, C is a point lies between A comma B. It is not equal to A as well as not equal to B. Therefore, C is in the form A plus theta H, where 0 less than theta less than 1. If we substitute theta, if you choose theta equal to 1, we get A plus H. That means the C value equal to B. But as per definition, C not equal to B. Therefore, we avoid 1. Theta value avoid 1. That means strictly less than 1. Similarly, C is not equal to A. If you put theta equal to 0, we get C value equal to A. But as per Lagrange's mean value theorem, C not equal to 0, not equal to A. Therefore, take 0 strictly less than theta, strictly less than 1. substituting in our Lagrange's mean value theorem of first form, f dash c. C value is here a plus theta h. Substitute c value. F of b. B value is a plus h minus f of a by b minus a. By taking first form and substitute c value and b value, we get the required form. Here the form is a get cancelled. A get cancelled in the denominator. B value is a plus h minus a get cancelled. We get in the denominator h. Take a cross multiplication. We get h into f dash of a plus theta h equal to f of a plus h minus f of a. So keep f of a plus h one side and move other factor other side. That means you remember that this is the f of a plus h equal to f of a plus h into f dash of a plus theta h. This is the second form of the Lagrange's mean value theorem. So comparing with the second form, first form is most important. If you know the first form, we can solve the second form of the problem also. So anyhow, we will see one more problem on the second form. First form, two kinds. Already we saw the first problem, second problem. They may ask those kind of problems. Find C value using Lagrange's mean value theorem. First kind. Second kind, so that the inequalities. Here also, by applying second form of the Lagrange's mean value theorem, show that, prove that, show that or prove that. Prove that log of 1 plus x equal to x by 1 plus theta x, where 0 less than theta less than 1. And hence deduce that x by 1 plus x less than log of 1 plus x less than x, where x greater than a. So apply the Lagrange's mean value theorem. But here also we required f of x value. So you think that it is in the form f of b, log b minus log a. Log a may be 0, log 1 maybe we expect that, because here we have a plus h form. A is 1. Log of 1 plus x minus log 1. Log 1 value is 0. That's why, therefore, we choose f of x value is log x. Based on the question only, we choose f of x. That's why these are the very tricky problems. If they provide f of x, find c is very easy. No need to think too much. Now, f dash of x value is 1 by, as per derivative principle, log x derivative is 1 by x. Immediately, whenever you see the f of x, immediately we need f dash of x. So we find f dash of x. Second form of Lagrange's mean value theorem is f of a plus h value equal to, this is the formula already we saw previously, f of a plus h equal to f of a plus h into f dash of a plus theta h. Now in our problem C, you understand that f of log of a plus h, that means a value is 1, b value is x. Choose a equal to 1, h equal to x. A equal to 1, h equal to x. F of 1 plus x equal to, just substitute a plus h in the formula. We get f of 1 plus x into f dash of 1 plus theta x. That implies f of 1 plus x equal to log of f of 1 plus x, nothing but log f of x equal to log x. Therefore, f of 1 plus x equal to log of 1 plus x in the left hand side. Right hand side log 1 plus x into 1 by 1 plus theta x. So f dash of x equal to 1 by x. Replace x with 1 plus theta x. We get this inequality. Log 1 is 0. So first part of the proof is over. For the second part, here we have two parts. This is the first part, this is the second part, and hence reduce that. This is the inequality. So this next we prove that the inequality. We choose theta value 0 lies between 0 and 1, because in the Lagrange's second mean value theorem, theta lies between 0 and 1. Now multiply with x. 0 less than theta x less than x. Sorry. Add plus 1 to the above inequality. 1 plus 0 becomes 1. 1 plus theta x less than 1 plus x, just like previous problem. Reciprocate 1 by 1 greater than 1 by 1 plus theta x greater than 1 by 1 plus x. Middle, this inequality write down in the less than format. Previously we write down left to right. Now we take in the previous, from the previous equation, you take right to left, we get a less than inequality. 1 by 1 plus x less than 1 by 1 plus theta x less than 1. Multiply with x above inequality. We get x by 1 plus x less than x by 1 plus theta x less than x. But we know this value, x by 1 plus theta x. Equation 1. Already we proved 1 x by 1 plus theta x equal to log of 1 plus x. Substitute this value. That means x by 1 plus x less than log of 1 plus x less than x. Where x greater than, because we always choose all values lies between a comma b. That means x we choose in between a comma b. That's why x is greater than a. Hence the problem. So I stop this video about Lagrange's mean value theorem. There is another mean value theorem, Cauchy's mean value theorem. Next video, I will prove the theorem. I mean, I provide the statement as well as problems based on the Cauchy's mean value theorem. Anyhow, comparing with Cauchy's mean value theorem, Lagrange's mean value theorem very, very important. In the examination point of view, you must practice all the problems Lagrange's mostly, then Cauchy. Okay. Shall I stop this video?